All right, so getting back into this. We are now in section 4.3. What we're going to be looking at is the derivative of the function e raised to the x. Now, there's a few things happening here that I want to point out. First, e to the x occurs here and e to the x occurs here, so we can factor that out. And we're going to get e to the x minus 1, because when we distribute e to the x back in, it comes back out to this, right? What's happening here is that for small values of delta x, for delta x approximately equal to 0, this thing is going to be on the order of 1 plus delta x. So what we're saying is, let me erase some of this. Tra la la la. What is happening here is we are making a substitution. We're saying if delta x is approximately 0. So delta x is between -1 and 1, somewhere in there, right? Then e to the x, e to the delta x, I mean, is approximately equal to 1 plus delta x. This happens for a couple different reasons. You could use what's called a Taylor expansion to get the same solution. You could use a bunch of different values to find out that it's approximately true. But what's really happening in an intuitive way is that at 0, this thing is 1, right? Now, at e to the 0 plus a small number, let's call it delta x, this is going to be 1 plus another small number, let's call it delta x. And that's what's happening intuitively, right? Is if this is a small number plus 0, then it's about 1 plus another small number. If you pick a small enough delta x, they're practically the same things. And that's what they're doing here. That is how we are moving from this line to this line. And now we're saying, hey, this 1 and this 1, they're going to cancel. So you're just going to have delta x over delta x. So the derivative of e to the x is itself. It's a weird function. It's one of the few that does this. I'm trying to think of any other functions that do. There's a few, but not many. This is pretty much the major one that we all care about. So what we are saying here is that dx of e to the x is equal to e to the x. This is why I asked that question at the very beginning about the limit definition and applying the derivative to it. I personally think this proof is a little bit easier to understand using the limit definition of E, but that's neither here nor there. Now, when we raise E to a function, because of chain rule, we're going to get E to the U times the derivative of U, right? So we're just going to apply chain rule again. Excuse me. of course, we need to require that u is a differentiable function. Now, what this means is that every tangent line of our function has a slope equal to the value of your function at that point. Which is kind of cool, actually. And it's because of this derivative behavior that mathematicians love E so much. If there was ever a rock star in mathematics as far as like functions that we like to see show up, e to the x is definitely one of them. So having said all of this, checking out a couple derivatives. Let's say we want to take the derivative of e to the 2x. Well, this is going to be the derivative with respect to u of e to the u, right? Times the derivative of 2x, where u is equal to 2x. So this thing is going to come out to be e to the u times 2. But u was equal to 2x, and we're going to bring out the 2 out front. So we're going to say 2 times e to the u is equal to 2 times e to the 2x. Now, on your own, try to work out c. We'll give you all 3 minutes to do that. Yep, C. I'll give you a hint. Your answer will have E in it. I don't know if that was sarcasm on your part or not. It was. Oh. Yeah, sorry.
Next time I need to.
We're just going to make signs. Hold up a little tab. Sarcasm.
So mistake.
So who got 18x squared times e raised to the x cubed? Anybody?
I looked at the slide. And I did.
So what we're going to do is we're going to say let u be equal to x cubed, then its derivative is going to be 3x squared, right? And e to the u, well, it's just going to differentiate out to be e to the u times du dx. Du dx is 3x squared. So we're going to have 6 times e x cubed times the quantity 3x squared, or 18x squared e to the x cubed. So to work this out on the board, just to kind of go through it step by step and let everyone see what it is I'm trying to say. That d dx of e to the x cubed this thing is going to be equal to d du of e to the u times d dx of x cubed, where u is equal to x cubed. Everybody agree? So from here, we're going to get e to the u times 3x squared. My mistake, I forgot the 6 out front, didn't I forgot the 6 out front. I did. So we're going to get 6 times e to the u times 3x squared, or 18x squared e to the u, but u is equal to x cubed. So that is 18x squared e to the x cubed.
Obviously, the way you explained it isn't valid, but I was maybe
No. Cool.
it was just your.
Good. This is actually why I go through the slides the way I do, is sometimes they explain more than I would, and other times they explain less. But I can at least touch on different details, right? Like, we're missing a step here. What is the step? To kind of fill in the blanks. Because again, personally, I hate it when professors lecture off the slides, and I try not to do that. But at the same time, I do think using slides is a good way of guiding the lecture. Okay. Now I'm going to be a sadist
Okay.
and give you some of these other functions. How are we going to handle these? First, b. What would you do with b? Because that looks like it could be the worst one, right?
Yes.
I want you to do b on the board. Come on. It's not going to be that
Last
bad.
time I talked in class,
No, it's not going to be that bad, I promise.
I feel like.
Is no, not at all. Not at all. Not at all. I actually gave this problem, I asked somebody to do this problem because this looks much more difficult than what it actually is. This is actually, of all of the problems up there, the easiest one to do, but it looks like the most difficult. And the reason why it's going to be the easiest is because we can factor out that 1/2. We can say, all right, cool. When we do that, the derivative of 1/2 times the quantity e to the x minus e to the negative x. Well, this thing's going to let us pull out that 1/2, right? So when we do that, this is all going to become 1/2 times d dx of e to the x minus e to the negative x. Right? So this is equal then to 1/2 the derivative of e to the x minus 1/2 the derivative of e to the negative x. Now do you see it? Well, the first one's pretty straightforward, right? It's just going to be e to the x. Agreed? Let's go ahead and write that. Equals 1/2 e to the x minus 1/2 d dx e to the negative x. Now think about what we did over here. This top example, what happened? That constant that we multiplied x by just essentially got pulled down, right? What we're going to find is the same thing happens here. That negative gets pulled down. Cool. So what you're going to have then, I'm going to work just the negative term over here. What you're going to have is d dx of e to the negative x. This thing is equal to d du of e to the u times d dx of negative x, where u is equal to negative x. Agreed? So if this is the case, well, this is going to come out to be e to the u. This is just going to come out to be -1, right? But u we just said was equal to negative x. So this is e to the negative x, the negative of that. It's negative e to the negative x. So this whole thing is now equal to 1/2 e to the x plus 1/2 e to the negative x, or e to the x plus e to the negative x over 2. Make sense? So all we did was pull out that 1/2 first. Yeah. Then, after factoring out that 1/2, we said, all right, this first term, that's straightforward. That's just e to the x. 1/2 times e to the x. The second term, and this is going to take some work. It's a like chain rule. We get negative e to the negative x. Minus the negative because plus is positive. And then putting everything back together, the 2 in the denominator. These are hyperbolic sine and hyperbolic cosine is what these two functions represent. The real form of hyperbolic cosine and hyperbolic sine. What's up? So I'm just going to zoom in really quick and show B. So notice they factored out the 1/2, just the same. They differentiated. They didn't quite explain how they differentiated, but it's the same idea. Right? Having said that, let's go back to the other problems. So this is, like I said, the easiest of them all, I think. This problem becomes pretty easy if you solve A. Or you could factor out e to the x. So I'm going to do A and B really quick. A says that the function f of x is equal to x times e to the x. Well, here we're gonna have to use product, right? The product rule. Agreed? And I didn't mean to embarrass you if I did. So just,
Never talking again.
I'm sorry. I know. I apologize. But what we're going to do is apply the product rule here, right? When we do that, we say, all right, cool. The derivative of x e to the x, this thing is equal to e to the x times the derivative of x plus x times the derivative of e to the x. Well, this thing's going to differentiate out to be 1, and this thing's going to differentiate out to be e to the x. So we get e to the x plus x times e to the x. So looking at D, we should just get x e to the x, right? Let's do D in a slightly different way. So we're told in B that our function g of x is equal to x e to the x minus e to the x. Well, this thing can be rewritten as e to the x times x minus 1. Now let's apply the product rule to that. Then d dx of e to the x times x minus 1 is equal to e to the x times the derivative of x minus 1 plus the quantity x minus 1 times the derivative of e to the x so this thing then, well, this thing is going to come out to be e to the x times 1, right? Plus x minus 1 times e to the x. Well, that first term was just e to the x. This can be expanded now into e to the x plus x e to the x minus e to the x. And we get just x e to the x. Notice the same thing would have happened if we just differentiated both terms individually, right? And in the case of C, what do we do? What do y'all think? What do we apply here? Should be the quotient rule, right? Yep. So really quickly looking through these, A did in fact come out to be x e to the x plus e to the x. B we already went over. C we're going to come back to, and D did in fact come out to be x e to the x. Now, C, we're just going to apply the quotient rule to this. So it's low, D high. Well, the derivative of e to the x is e to the x. So we have x times e to the x minus high, D low. Well, the derivative of x is just 1. So we have e to the x divided by the square of what's below x squared. And here we can factor out e to the x. So we get e to the x times the quantity x minus 1, all divided by x squared. Make sense what I mean? So these aren't nearly as difficult as what they actually look like, right? These take some time to work with and some thinking about, sure. But like you said, in B, we did have some cancellations, right? Like we had that negative sign cancel out to be a positive sign in the end. So already you were on the right track in that sense. And that's kind of what I'm trying to point out with all of this is that e to the x makes a lot of our derivatives really nice. It makes a lot of our math really quick to do. You see e to the x and you can run through those derivatives pretty quick. That said, it's not always the case that it's going to be immediately obvious how to handle this, like here. I want to make a point here. This problem, we've already done an analogous formula. This problem is pretty much exactly what I just asked on the board. Except instead of 1, it's 1 over 60. Instead of -1, it's 1 over 60, or negative 1 over 60. And instead of 2, instead of multiplying by 1/2, we're multiplying by 30. So it's the exact same problem, just different constants. Now this is actually another cool problem from this class that has applications in the real world. This is exactly how power lines hang, or whatever that's worth. This isn't a made-up problem. This is exactly the formula that defines how they hang, which I personally think is kind of cool. And just to show you all what that looks like, if you could go out forever. That e to the x plus e raised to the negative x. Stop that share. Let's share the calculator. Looks like that. Looks almost like a parabola. So let's compare it to a parabola really quick. New equation. So now in black is the parabola, and gray is the canary line, canary, whatever it is. It's not quite the same. There are some differences here. First, your function x squared is less than Cantry up to 1. No, my mistake. It's not up to 1. It's up to like the square root of 2, I think. Maybe. It's up to this value here, wherever that is. And then it's greater than after that. So just something that's kind of interesting to note about that. And since we've already seen it, the derivative of that it's y, that's y. And what that other function, the derivative of that e to the x plus e to the negative x looks like, it's like that. Just some interesting details about all of these. Now, not there. That is what I wanted to click on. Getting back to the lecture. I can do this the right way. There we go. So in this case, the problem just wants to know how much does the wire sag between the two and what's the lowest point midway. So how are we going to find midway? We're going to take the derivative here and set it equal to 0, right? And then, well, let me step back. Because what we want to show is that the lowest point on the wire is midway, we're going to take the derivative, set it equal to 0. If it has multiple zeros, we're going to check which one of those zeros is lower than the other ones, right? Because the lowest point should have a derivative of 0, and we're going to have to check the boundaries. Does that make sense what I mean? Then we're going to say, all right, cool. In this case, we have only one time when this has derivative equal to 0. That happens to be at x equal to 0, which we can see here, because when this x is 0, this whole thing becomes 1. When this x is 0, this whole thing becomes 1. So we get 2 times 30 is 60, and we can compare all the other values if we wanted to around that. But again, we would take this derivative, set it equal to 0, find that it's equal to 0 when x is equal to 30. Then we'd say, what is that value? We just calculated out from the 60. Now, what's our values at the ends? And take the difference. And that's what they've done here. Maximum revenue. So here we have another case where it's the demand function, so we're gonna have to multiply this by x, right? We're gonna get x times 56 e raised to the negative 0.000012x. And graphically, it's going to look like this. And we want to find the max. So we're going to take the derivative, set it equal to 0. Find the x value that corresponds to that. Plug that x value back in to our original demand function to get price out. And finally, one last example of where this stuff shows up. Normal distribution functions. This is another one of those functions that dominates your life right now, dominates your life in general, but especially right now since we've been talking about the pandemic and vaccines for so long, right? And one of the things that we have to look at when talking about vaccines is the efficacy. And one of the functions they use to talk about efficacy, to understand probabilities and statistics, etc., is this normal distribution function, or the normal probability density function, which you all are familiar with. This is everybody's favorite ghost function. I call it the ghost function because it kind of looks like a ghost, like a kid in a sheep, right? Like that's what it always reminded me of. But again, I just really quickly wanted to touch on all of these, just so that y'all have some idea of what these problems are about, what they look like, how to go about them. I do expect y'all to, on your own at home, touch on these a little bit, to go back and look at some of these problems. We just don't have time to go through all of them. Having said that, I do not have enough time to jump into the next section. So I will let you all go. If you have any questions, I'll stick around.